Right. Good evening, students. In the last class, we have completed till here the properties of gases and properties of gas mixture. This part of syllabus is now completed. Now, let us start the concept of thermodynamic relations. In this, we will see the Maxwell relations, TDS equations, Clapeyron equation, and Joule-Thomson coefficient. These are the four topics we are going to see. So thermodynamic relations are very important in the sense that they relate the various properties here. That is, you have properties like pressure, temperature, volume, entropy, and stuff like that. All these things are appropriately related with each other. All these thermodynamic properties are related here in the Maxwell relations, especially. So, how is that done, and all we are going to see. So, first of all, let us look at the Maxwell relations. When it comes to the Maxwell relations, in Maxwell relations, we will basically have four number of equations. Four numbers of Maxwell relations. They are, let us say, M1, M2, M3, M4. Maxwell relation 1, Maxwell relation 2, Maxwell relation 3, Maxwell relation 4. These are the four relations that you will have, and M1 will be dependent on U, that is your internal energy. M2 will be based on H, that is enthalpy. M3 will be dependent on F. This is called as Helmholtz function. Basically, what is Helmholtz function and all we will see when we go to M3 directly, and M4 is G. G is nothing but the Gibbs function. So U is internal energy, H is enthalpy, F is Helmholtz function, and Z is Gibbs function. So by now we must be knowing what is internal energy and enthalpy. Helmholtz function and Gibbs function I will be telling you shortly when I go to the discussion of M3 and M4. But at the outset we must understand that Maxwell relation 1 is dependent on internal energy. Maxwell relation 2 is dependent on H. 3 and 4 are respectively dependent on F and G, that is Helmholtz function and Gibbs function. Okay, so this is the thing that we should know at the beginning. Let us now jump into M1, that is Maxwell relation 1, M1. So this will be dependent on your internal energy U. So how do I write internal energy here? The internal energy I will be writing in this form. So basically, I know first law of thermodynamics, dq is equal to du plus dw. This formula I know. So from this I can write du is equal to dq minus dw. So here, based on Clausius inequality, I can write that dq is equal to tds, and in place of dw I can write p dv, that is nothing but the work done, that is the displacement work formula. So this is how I can write the U formula here. Okay, so if I know this U formula based on the principles of partial differential equations or the theorems in the maths theorem, I know that if a given property is like this, that is dz is equal to m dx plus n dy. If this is the case, then if I take the partial differentiation form of this expression, that can be like this: dou m by dou x no, it's not dou m by dou x, dou m by dou y at constant x, will be equal to dou n by dou x at constant y. So this is what the partial differential equation principle or the mathematics theorem says to us. So based on this expression, if I apply it here for this du, what I am going to get here is, in place of m, I have t. So I can write dou t in the numerator, and in place of y, I have dv here. So I can write dou t by dou v here, that too at constant s, s being your x here. In place of s you have x here, that's why s I am taking it as constant here. Similarly, on the other side, if I go, I have dou p here. In place of my n I have dou p, and in place of my x I have dou s, in place of my y I have v. So this relationship is nothing but your Maxwell relationship 1. This is called as M1. This relationship is nothing but your M1, that is Maxwell relation 1. So now we will move to the Maxwell relation 2, M2. And we already said that M2 will be depending on your enthalpy, that is H. So if I write H here, this H will be equal to U plus PV. By definition, H is nothing but U plus PV. So if I apply differentiation on this side, dH will be equal to dH will be equal to du plus P dV plus V dP. And this expression that I am seeing here, this du plus pdv, is nothing but dq. Why? Since your dq is equal to du plus dw based on your first law of thermodynamics. So based on this, what I can do here is dH can be written as, in place of du plus pdv, I can directly write tds. Why? Because dq is nothing but my tds. du plus pdv can also be written as tds. So it's the same thing, tds I have written here, plus vdp. So now your expression dH is now in the form of tds into vdp, and here I have my mathematics formula. Based on this, I can write this expression also similar to the one that I have written for M1. M2, now I can convert it into this form. In place of M I have T, so I have dou T here, and in place of Y I have P here, so I will have dou P here. I think in the previous thing I should have a minus here. I have somehow missed it. I'm really sorry for this. Kindly note that there is a minus here. This side in the mass theorem I have plus, and towards my left here I have minus, so I should include minus here or on the other side. So I'm including it here. Kindly correct the same. So now let us look at this expression. Dou t by dou p at constant s will be equal to dou v, because my n is v now, dou v, and my x is s now, dou s of p. So this expression will be my expression for m2. This is a Maxwell relation 2. So far we have seen two Maxwell relations, Maxwell relation 1 and Maxwell relation 2. Now we will move on to the Maxwell relation 3. So the Maxwell relation 3 will be dependent on your f. Okay, I think I must tell you this thing here. So first thing you remember here, u, and the remaining is hfg. So remember this as hfg or uhfg, you remember like that. So now let us come to f. This m3 is dependent on f, we said. What is f? F is nothing but Helmholtz function. What is Helmholtz function? Like you have related h is equal to u plus pv, similarly you can relate u minus ts. So you take the expression of this u minus ts, this will be a property in thermodynamics. So you have given it a name called as f. Someone named Helmholtz actually found out this. He has discovered this. That's why it is called as Helmholtz function. So f is equal to u minus ts is the definition for the Helmholtz function. And now I will differentiate by applying d on my left and on my right as well. So du minus tds. See, I am doing uv whole dash here, u dash v plus v dash u I am doing. So that will be t into ds minus s into dt I will get here. So the same df can also be written as, in place of this u du minus tds, I can actually write pdv. So how I will write that, I will show you here towards my left. Observe this, towards my right I should say. So I know that from my first law of thermodynamics, dq is equal to du plus dw. So dw can be written as dq minus du. And from the Clausius inequality, I know that dq is tds and du I will write it as it is. And dw is nothing but pdv. pdv. Now I will apply minus on both sides. I will get minus pdv equal to du minus tds. So based on this expression, you can see that du minus tds is nothing but pdv that I got here. This is minus pdv. So the same thing I can substitute it here, minus pdv minus s dt. Okay. Also I have my maths theorem, which I have already shown to you previously. Based on this maths theorem, I can write this expression df in this form. See, the minus that is there here will get cancelled out on the both sides. In place of m, I have p here, so I can write dou p. This p is not so nice, so I will just change it. Dou p, and in place of y, I have t here. Dou p by dou t I will have. And in place of my x, I have v here. So at constant v I will have. And then what happened? And then I have, in place of n I have s, so I have dou s. And in place of x I have v, so dou s by dou v. So this is dou s by dou v on constant t. So dou p by dou t at constant v is equal to dou s by dou v at constant t. So that's what I have as my Maxwell relation 3. So this is my m3. Okay. So this is my m3. So Maxwell relations are essentially a partial differential equations. They are not definite differential equations. So you have dose here, you don't have d's here, so have that in mind. Now we are done with M3. We will now move on to the discussion of M4, that is Maxwell relation 4. This Maxwell relation 4, I said, is dependent on G, that is Gibbs function. What is this Gibbs function? By definition, the Gibbs function G is equal to H minus Ts. Like you have said, H is equal to U plus PV, F is equal to U minus Ts. Here you are saying Gibbs function, which is H minus Ts. So H minus Ts is found out to be a property of the thermodynamic system by a person called Gibbs. That's why you name it as Gibbs function. G is equal to H minus Ts. Now here I'll apply d on both sides. Dg will be equal to dh minus uv whole dash, which is nothing but tds minus s dt, and this dg will be equal to this. I can write it as vdp. How I will show it to you on the other side here. Since h is equal to u plus pv, I can write that dh is equal to a du plus pdv plus vdp, and this du plus pdv is nothing but dq plus dw plus vdp. So this dq plus dw, sorry, I think I should write du plus dw here. So this du plus dw is nothing but my dq plus vdp I will get here. So on my left, what I have is my dh. So now if I transform this expression dh minus dq will be vdp, and I can write that vdp is equal to dh minus, in place of dq I can write tds based on my Clausius inequality. This is a simple transformation of my h is equal to u plus pv. So in the place of dh minus tds I can write vdp now. So here I'll get vdp minus s dt. So this is my expression for dg. I also have my maths formula or the PDE formula. So based on this PDE formula, in place of my m, I have v here. So I can write dou v by, in place of y, I have t here. So dou t I will have. The constant x place I have p. So that is dou v by dou t at constant p, equal to dou, in place of n I have s here, dou s, and in place of x I have p here, so I should write dou p, and in place of y I have I have temperature, so I can write T here. Okay, so dou v by dou t at constant P is equal to dou S by dou P at constant temperature. So that will be my M4. Okay, so this is nothing but my Maxwell relation 4. M4. Okay, this is my M4. So far we have seen Maxwell relations. Let us try to summarize them quickly. Summary of Maxwell relations. So M1, the Maxwell relation 1 gives me dou t by dou dou t by dou v at constant s. will be equal to minus of dou P by, sorry, that is looking like a row. Now it's clear, dou P by dou it at constant volume. I think I made a little mistake here. I should add a minus here. Why should I add a minus here? Because there is a minus right here. So because of this minus, I should have minus in my M4. Kindly correct that. And then I have my M2 now. So this M2, we got it as dou T by dou P at constant S is equal to dou V by dou S at constant P. And I got M3 also, and this M3 is dou P by dou T at constant volume will be equal to dou S by dou V at constant temperature. And I got M4 also. This M4 is dou V by dou T at constant pressure equal to dou S by dou P at constant temperature. There is minus here. So you remember that M4 and M1 will have minus symbols. Okay, so here you have minus for M1. You can observe that there is a minus here. Likewise, you will also have minus here for M4. So you remember that there will be minus for M1 and M4, and the remaining things you will not have. And these things are dependent on UHFZ. So that's how you will understand the Maxwell relations. So once we're done with the Maxwell relations, the next concept that we have here is the TDS relations. TDS relations. See, you have Maxwell relations numbered 4. Here you have two numbers of TDS relations. If Maxwell relations are 4, TDS relations or TDS equations also people say it. Equations are generally used in your syllabus. So let me use the same thing here. So the TDS equations are two numbers, and these two numbers, if you look at the TDS1, let me call this TDS equation 1. Okay, I'll write it as TDS1. This is based on temperature and volume. And you have TDS equation 2, TDS2, which is based on temperature and pressure. So you understand the difference here. This is temperature and volume, temperature and pressure. So in both the things, temperature is common because you have temperature here, but one you will have volume, two you will have pressure. That is the thing here. So in order to derive the TDS1 expression, TDS1 expression, so what we will do is we will consider that the entropy is a function of temperature and volume. Like we have said here, the entropy is a function of temperature and volume. So if this is the case, we know that from the principles of my differential equations, and especially the partial differential equations, for this kind of cases, I can write that ds will be equal to dou s by dou t at constant volume into dt plus dou s by dou t, sorry, dou v at constant temperature into dv. So this is how you can write the expression. So this expression that you have written here is actually based on the principles of partial differential equations. So this expression, now I will transform it into TDS equations by multiplying with T on both sides. So if I do that, TDS will be equal to T into dou S by dou T of V into dt plus dou S by dou V of T into dV. So this is how your expression will turn out to be. So to write it in simple terms, let us transform this right hand side. So this right hand side, I'll call this part as my A and this part as my B. So let us deal with A first. Okay, if I deal with my A here, now to deal that, I will make use of my CV here. Okay, how I will do that, you will understand. You keep observing the CV. By definition, you know that du by dt, yet constant volume. CV is definitely said for the constant volume process, so this will be a constant volume here. So that's the CV. This CV can be transformed in terms of ds. For that, what I will do, I will make use of again my first law of thermodynamics. Dq is equal to du plus dw here. So this dq is nothing but my tds as per my Clausius inequality, and du I will have here, and then pdv I will write here. So this pdv which I have here is nothing but 0, because this is a constant volume process, we say. Okay, because v is constant here, at least in the part A. So especially in the part A, your V is constant. So du now can be written in the form of TDS. So what I have here in the numerator can now be replaced into this form. So the CV is equal to T into dou S, I will write here because I am taking it as a partial derivative. That is, only one thing is constant at this place. So that is, only volume is constant in this expression. So I will use dou here, dou S by dou T, yet constant volume I will take. So this is my CV here. If you observe the expression A carefully here, this part, the first two terms is nothing but my CV now. So what I can write here is, if I write CV into dt, that will be, that is, I'm multiplying dt on both sides, t into dou s by dou t at constant v into dt I will do. So what I'm trying to tell you is, here my whole expression of a can be simply written in terms of my cv into dt. The cv into dt, that's the issue with pen, don't worry, cv into dt. So the cv into dt is nothing but the expression of a. So you can substitute this a into your TDS1 expression. Also now deal with b now. If you deal with b, here to deal with b, I will make use of M3, that is a Maxwell relation 3. So the Maxwell relation 3, what I have is dou S by dou V at constant temperature is equal to dou S by dou P at, sorry, dou P by dou T at constant volume. So for this one, I will multiply T on both sides. Better to do TdV multiply TdV on both sides. So what I will get is T into dou S by dou V at constant temperature into dV is nothing but T into dou P by dou T at constant V into dV. So on both sides I have simply multiplied it with TdV. So if I do that, you look at this expression of my B here. This in this expression of B, I should actually have T here, because I have multiplied it completely. I should have T here as well. So T into dou S by dou V of T into dV, that you have on my left hand side, is nothing but T into dou P by dou T at constant V into dV. So now if you substitute A and B in the TdS expression, so your TdS expression will now take the form of Cv into dt plus T into dou P by dou T at constant volume into dV. So this is nothing but your TdS1 expression, TdS1 equation, I can say. So this is the TdS1 equation. If you observe this carefully, here you have only the constant volume thing. This is also a constant volume thing. So what we have said in the beginning is, yes, that is entropy is function of only temperature and volume. So in the same fashion we have converted it, so that the complete expression will be in the constant volumes, in terms of constant volumes. So and the appropriate changes can be accounted for in this equation, that is the TdS1 equation. Now that we have done that, we will now move to the TdS2 expression. So here we will be considering S as S of temperature and pressure, so that entropy will be the function of only temperature and pressure. For this, now I can write that the ds is equal to, similar to what I have done to the TdS1, I am doing the same thing, dou S by dou T at constant P into dt plus dou S by dou P at constant T into dP. So this expression I will get based on the partial differential equation. Principles of partial differential equation, you can write this expression like this, and even your units will balance accordingly in this particular fashion. Then if I go forward and multiply with T on both sides, I will get my TdS. What I want here is ultimately TdS. This TdS will be equal to now T into dou S by dou T at constant P into dt plus T into dou S by dou P at constant T into dP. Okay, so this is my expression here, and now in order to transform it properly, let me call this as C, let me call this as D, C and D. So if I keep transforming my C, for this I will make use of Cp here. Cp is equal to dH by dt at constant pressure, we know this already, and the Cp is equal to, in terms of, I can write as TdS here also. How I'll get that, I'll show you here. So if I take H is equal to U plus PV here, then I can take dH equal to U du plus PdV plus VdP, and dH will be equal to du plus PdV is nothing but du plus dW. Du plus dW is nothing but dQ plus V dp. This expression I have here, and in this expression I can make this as 0 because I am speaking about a constant pressure process here. As far as C is concerned, this is a constant pressure process, so I can make that part as 0. So dH will now become dq. dH is nothing but dq. This dq can be written as TdS. So in place of dH here, I can put T and ds. I'm writing it as dou s because I am interested in the partial differential form. Okay, what I have in the C is my partial differential form, so I will write that as T into dou s by dou T at constant pressure. Okay, since I have dt here, I will multiply dt on both sides here. So Cp into dt will be equal to T into dou S by dou T at constant pressure into dt. So this is how I will get for my C. Now I will proceed to my D. So for my D, I will do the transformation, the mathematical transformation I will do here. So for this purpose, I will be making use of the Maxwell relation again. So it's appropriate to use the Maxwell relation 4 here. So based on M4, based on Maxwell relation 4, I can say that dou V by dou T at constant pressure is equal to, minus is there here, this is very important, we should not miss this, dou S by dou P at constant temperature. So this is what I have here. The same expression can be uh, transformed here in order to get this dou S by dou P in the positive form. So what I can have here is dou S by dou P at constant temperature will be equal to minus of dou V by dou T at constant pressure. So simply I have taken the minus onto the other side, that's it. So this is the expression I have, and in order to further transform it, I will multiply with TdP on both sides. So if I do that, what I'll get here is T into dou S by dou P at constant temperature into dP is equal to minus of temperature into dou V by dou T at constant pressure into dP. So if I substitute these two in my TdS expression, substituting A, sorry, this is not A, this is C and D. Substituting C and D in my TdS expression, I'm going to get that TdS equal to Cp dt minus, this minus is very important, so don't miss this minus, T into dou V by dou T at P, at constant P into dP. This is how you will get your TdS2 expression here. This expression is TdS2. Two expression. So if you observe carefully here, in this particular expression you have all constant pressures. This is at constant pressure and this is also constant pressure. So previous expression is constant volume expression for TdS. This is the constant pressure expression for TdS. These are the two TdS equations that you should keep in mind. So I think with this I will close this lecture here, and I'll continue the remaining part of Joule-Thomson effect and Joule-Thomson coefficient and the remaining topics in the next class. Thank you.